Hello, Chem 1B. This is Chapter 16, Lecture Video 1. So this chapter is going to be about acid-base equilibrium. And so we're going to kind of continue where we left off in Chapter 15, but now we're going to get way more specific, specifically talking about just acid-base reactions and how they work. So in Chem 1A, you probably learned at least two of the three primary definitions for acids and bases. The ones at least I cover in Chem 1A are the Arrhenius definition and the Bronsted-Lowry definition. So Arrhenius basically, we'll go into these a little bit more, but a gist is Arrhenius is all about that acids increase H plus concentration and OH minus, and bases increase OH minus concentration. The Bronsted-Lowry acid-base definition is all about what we call the transfer of a proton. So, or in other words, an H plus atom or ion. The third and final definition is known as the Lewis acid-base definition, and it is something we'll cover at the very end of this chapter, is the most general type of definition. It basically says any compound that can donate or accept electrons is either a Lewis acid or a Lewis base. So let's go into the first two a little bit more. So the Arrhenius acid definition is that an Arrhenius acid is a substance that increases the concentration of H plus ions in water, like HCl. If I dissolve HCl in water, it will ionize, because it's a strong acid, into H plus and Cl minus, thereby increasing the H plus concentration and making it an Arrhenius acid. At the same time, on the other side of this coin, Arrhenius bases are substances that increase the concentration of OH minus ions in water again. Pretty much the same definition, but now we're talking about OH instead of H plus. So NaOH is an Arrhenius base because when we dissolve it in water, it breaks apart into Na plus and OH minus, increasing the OH minus concentration in water, making it a base. Now, this is pretty much probably one of the more simplistic definitions of acid-base chemistry. However, it's also the most specific, right? It has to be a substance that increases H plus in water. So we can only be in aqueous solutions when we're talking about Arrhenius acids and bases. This is a little bit of a limitation of this definition, which brings us to the more used definition, at least in Chem 1B, and that is the Bronsted-Lowry acid and base definition. This definition states that a Bronsted-Lowry acid is a substance that donates a proton. In other words, an H plus ion. Now, the word proton often gets confused, H plus and proton. What's going on there? If you think about a hydrogen atom, a single atom of hydrogen contains one proton and one electron. So if it's H plus, it's lost its one electron, making it just a single proton. Hence the word proton used here. At the same time, a Bronsted-Lowry base is a substance that accepts a proton. So the acid donates the H plus, the base accepts the H plus. What this means is that every Bronsted-Lowry acid reaction is going to have an acid and a base component. And really what's going on is the H plus is getting handed off from one substance, the acid, to the other substance in the reaction, the base. So really all a Bronsted-Lowry acid definition is stating is that acids and bases, they transfer protons from one to the other. So if we look at this reaction, we have HCl reacting with NH3 to give us NH4 plus and Cl minus. Now, this is an acid-base reaction, and we can define which one's the Bronsted-Lowry acid and which one's the Bronsted-Lowry base. Now we can tell where the proton went and where it was donated from and where it was attached to by looking at the products here. Now, we know that originally there was a hydrogen on HCl, so there was a hydrogen attached to the Cl here. But on the product side, we notice that Cl is by itself. Right, Cl minus now. That means the HCl must have donated H plus. So it's going to be our Bronsted-Lowry acid. At the same time, well, there's really only other one option for the base, which has to be NH3, but we can see that it's also the base because it initially has 3 hydrogens here, and on the other side has 4, meaning it accepted an additional proton. This means our HCl is the Bronsted-Lowry acid, and our NH3 is the Bronsted-Lowry base. Now, that is all I cover when I teach Chem 1A, at least, for acid-base definitions. We're going to go a little bit more in depth into Bronsted-Lowry. Bronsted-Lowry continues with what we call conjugate acid-base pairs. Now, the conjugate acid or base of the opposite of that word differ only by the presence or absence of a proton. In other words, they're a pair. So if we think about HX, it's a weak acid. It has a strong acid. It's an acid. It has a conjugate base. If we have a base, it has a conjugate acid. Now, really the difference between the two pairs are the presence of the H. So if that H is donated, like acids do, right? It donates an H plus somewhere to something, right? Then what's left is the conjugate base. So in other words, the H plus goes away. What do we have left? In HX's case, we have X minus. And this would be the conjugate base of HX. So let's label the acid and its conjugate base in the following reaction. So if we look at HX, notice it donated its hydrogen to water, forming H3O plus, and it became X minus. What this means is that HX is our acid because it donated its proton, and X minus is its conjugate base. These two make what we call a conjugate pair. However, in every Bronsted-Lowry acid-base reaction, there's always a base and an acid. By this definition, water, normally considered neutral, is actually acting as a base in this case, because as you can see, the hydrogen got donated to water. Well, if water accepted that hydrogen, which it did because it became H3O plus, then that makes water also a base in this case. And its conjugate acid is H3O plus. And these two make our second conjugate pair. Now we need to be able to determine what the conjugate acid of a given thing is and what its conjugate base is, or vice versa. One thing to know is that not all acids are positive, right? The H plus going away leaves a negative value. It could be positive or negative for all our different substances, acids or bases. It really just depends on the compound. All Bronsted-Lowry acids are proton donors though, meaning they give up their hydrogen. And all Bronsted-Lowry bases are proton acceptors, meaning they add on a hydrogen on the opposite side of the reaction arrow, or the product side. So let's do a little bit of practice here. So if we have, say, NH3, right, let's write its conjugate acid. Well, the conjugate acid of NH3 would be NH3 plus one more hydrogen, or in other words, NH4 plus. While the conjugate base of NH3 would be the opposite. Instead of gaining a hydrogen, we're losing a hydrogen. So this would be NH2 minus. And we can do this for the others as well, right? H2O, its conjugate acid would be H3O plus. And its conjugate base would be OH minus. H2PO4, its conjugate acid is H3PO4. And its conjugate base is HPO4 2 minus. OH, its conjugate acid, again, we're gaining a hydrogen, would be H2O. Its conjugate base, losing the hydrogen, would be O2 2 minus. Or sorry, just O2 minus. My bad. Not peroxide. O2 minus. So you can kind of see how this works, hopefully. So let's continue on a little bit more. So again, this idea of conjugate acid pairing, there's always a base, there's always an acid, and there's always a conjugate base and a conjugate acid in any Bronsted-Lowry type reaction. So if we look at this whole group here, there's something special that tends to happen here, and you might notice it. In one of these reactions, water is acting as a base. But in the second reaction here, water is acting as an acid. This ability of water to act as either an acid or a base in any given acid-base reaction is what we call amphoteric. Water is an amphoteric species, meaning it can act as either an acid or a base. This is true of many different substances as well, other than just water. But water is by far the one we see most often. So the other group that are amphoteric are anions of polyprotic acids. Now, polyprotic acids might be a new word for you. Polyprotic effectively means that we have more than one hydrogen attached to our acid, right? So this acid, sulfuric acid, is diprotic because it has two hydrogens attached to it. If we look at phosphoric acid, H3PO4, it would be triprotic or polyprotic. Polyprotic just means more than one, many hydrogens attached. And the anions of a polyprotic acid, i.e. this guy here, HSO4 minus, or HCO3 minus, again, the conjugate of H2CO3. These anions are definitely amphoteric. So in this example here up top with the carbonate or bicarbonate or hydrogen carbonate, it's acting as a base. But in an equivalent reaction, we also have our bicarbonate acting as an acid. This ability to be amphoteric is pretty special, just based on the conditions depending on what's going on. A substance that's amphoteric might be an acid or it might be a base. Often on acid-base spills in the laboratory, we would throw down sodium bicarbonate in either condition, whether it's an acid spill or a base spill. Sodium bicarbonate will usually neutralize both because of its ability to be amphoteric. So let's do a quick little problem, and this will be the end of the video. Identify a conjugate acid-base pair in this reaction. All right, so if we look at these two, we know that this guy here is what? Well, we got to figure out whether this is the acid or base. And the same thing for water. Is this an acid or a base in this problem or in this reaction? Well, we determine this by looking at our products, right? What happened to this guy on this side? Well, it became this thing. And if we look, we have two hydrogens here on the reactant side, but on the product side, we now have three hydrogens. This tells me that CH3NH2 gained a hydrogen, or in other words, accepted a proton, making it the Bronsted-Lowry base. And this, its conjugate acid. So if the CH3NH2 is a base, then H2O must have been behaving as an acid. And we can see that as well. It's donating its hydrogen to there and forming OH minus. It lost its hydrogen. This means H2O is acting as an acid in this scenario, and OH minus is our conjugate base of H2O. So this says that this guy's the acid and this guy's the conjugate base, which is not true. It's the opposite of that, right? CH3NH2 and H2O are not conjugates of each other, and they're actually switched. This isn't the acid and this isn't the base. It's the opposite. This is my acid because it's the conjugate acid here, and this is my base because it's the base. So C is actually our correct answer here. And if we look at these two, again, these are not conjugates of each other. So C is the correct answer. All right, So if you have any questions about conjugate acid-base pairs or just acid definitions in general, please let me know. You can always reach me during my discussion sessions or my email.